Okay, so last time we finished lecture with the proof of one quite complicated theorem about the derived category of a ring. And we used some transfinite recursion, transfinite induction to prove it. And today the goal was to show that in general, well, the first goal, of course, there are many goals, but the first goal was to show that so this is the result of the Gabriel-Papescu theorem. Well, this is purely a result of abelian categories. There is nothing derived in this statement. Remember, this is an abelian category which has the exact filter colimits and the generator. So let me also give a notation for the generator. So G A ring is by definition the endomorphism ring of the generator. So then we have a canonical functor. I'm going to call this I. Functor which is from the category A, given abelian category, to the category of R modules, some object A, so notice that I can try to use different fonts for the category and for the object, so A is an object. So this is just by definition will be home from the generator to this given object A. So A is an object in the category A. So the home, of course, in the category, Grothendieck category A.
Сейчас это левый модуль. Эндоморфизм. Сейчас не было. А что?
I think that's right. Yeah, I think that's right. So opposite maybe. Check this. Okay. So then you can use something like a special adjoint functor theorem and show that for this functor I, defined like this, there is a left adjoint. So I has a left adjoint. I'm going to call this Q. So Q will be a functor from the right modules to the category E. So it exists by special adjoint functor theorem. You also can kind of give this functor a formula, and you can interpret this formula, convince yourself that this makes sense. And since this functor is a home functor, the adjoint functor has to be a tensor product functor. So if I want to compute this functor Q on some module, so in this formula M is the right module. Right, so then this will be the tensor product. So the tensor product of the M and the generator over the ring R. To see that this is true, well, for example, you can kind of check that the adjoint functor on the free module is just the several copies of the generator, and then you take any module and choose the free presentation of this module and use this functor. So this functor Q is a left adjoint, so it preserves colimits. Is this enough? Looks like I want the yeah, so definitely colimits is fine, yes. So what if you don't like this formula, you can ignore this. It's the rest doesn't depend on this special specific formula for the left adjoint. Okay. So now I want to look at the following diagram of R modules. I take module M, so it's kind of this is the key diagram for the rest of this kind of subsection. So I have module, which is a submodule in the home from G to some object A. So I'm going to have two objects, A and B. These are objects in the Grothendieck category A. And I also choose a map of modules F to the home over A from G to the B. So this is diagram in the category of the right modules. So I also want to fix notation for the coproduct coprojections. So the G has a map, say UM, to the direct sum over M of the G for the generators. So then, using this kind of diagram, I want to define two maps. So the map, so we define first map psi, which is from the direct sum of the generators taken over module M. I consider module M as just a set to the object A. So that's of course a map in the category A, and this is defined by the formula. Well, if this is a map from the coproduct, so it's enough to specify composition with the coprojections, and I just say that this is by definition. That's the way I define this map, right? So recall that little m is an element in the module M, and we consider this M to be a submodule in the home GA. So little m has an interpretation as a map from the G to the A. So in this way, this makes sense. And I have another map. So define psi and also pi, which will be again from the direct sum of the generator with itself m times to now to the object B. And this is defined by similar formula. Again, I need to specify the compositions with the coprojections UM. And now I just say that this is by definition F applied to the M, right? So when I have M, it's an element here, apply F, I'll get the map from the G to the B. So this is the way I define the map Y. I want to say that in this whole subsection of Gabriel-Popescu theorem, this will be kind of sequences of trivialities, but you just need to kind of make sense of every triviality. So for example, this is the definition of the two maps, pi and psi, which is kind of tautological, but you need to think about these definitions and be sure that this makes sense to you. Okay, so first lemma is that the map phi factors through image of the map psi. So to be more precise, now the statement of this lemma, so in the beginning of the proof, I'm going to draw a commutative diagram that kind of explains what I mean by this statement. Well, I have direct sum of generator G, M times with itself. So then there is a map psi to the object A. Now I also want to introduce notation K. This will be the kernel of the psi. So here there's also the embedding of the kernel into the direct sum, and I want to call this map mu. Okay, and also there is a map somewhere here which I called phi. This is a map from the same direct sum to the object mu, right? So actually the statement and the thing I'm going to show is not just the it's the equivalent thing. Instead of saying that the map phi factors through the image, so there's like somehow image of the psi, which is have an epimorphism from this sum, and this is embedded into the A. But equivalently, I can say, so the lemma that I want to show is equivalent to statement that the composition of the phi and mu is 0, right? That's the same thing. Okay, so that's the goal. Okay, to do this, I'm going to use that A is a Grothendieck category, and the first thing I want to consider the pullback diagram. So K prime F this will be defined as a pullback. So let me take F. So in this diagram, F is a finite subset. So then I have when I write direct sum over F, I just mean this is some finite direct sum over elements in the F, just for shortness of denotation. So then there is of course a map to the direct sum of the G. So I'm going to use notation for this map, the sum of the, again, taking over finite set F, UM, PM. So this PM is just the direct sum. M is in the F of the G, and then there is a projection PM to the G.
What is K sub F prime?
I'm trying to define this. I want to say that this is a pullback, and I'm drawing a diagram, so I'm going to need to specify one more map, an object. So here, the object is just the kernel, and the map is, of course, mu. So that's the kind of diagram that is already given, and then I take the pullback, call this lambda F, call this maybe mu prime. Right, so that's a pullback diagram. So pullback. Two ways to specify this. I'm now saying it's pullback, writing PB and writing also this symbol. So that's a pullback. And this is how we define K prime. Okay. So now I want to do the following. Well, first of all, I want to do two kind of reductions. So first of all, I want to say that it is enough to show that the composition of the phi and mu, and I also take composition now with lambda F is 0 for any F in the M finite. Sorry, I need to show that this claim is correct. So suppose I know that I have this for any finite F, and then I need to show that this composition of the phi and mu is equal to 0. Right, this is done by using that we have a Grothendieck category. So first of all, the kernel K, well, I can clearly write this as follows. Right, so that's a sub-object in the direct sum. I intersect the sub-object with the object, I just get the same sub-object. Now, this direct sum over M, I can write this a little bit differently. I can say that this is kind of sum over all the finite subsets, and then for each finite subset I have finite sum. So this is still the same direct sum over M. Now, since I'm in the Grothendieck category, I can rewrite this as the sum over all finite subsets. Now I take the intersection of this. That's one of the properties of the Grothendieck category that can be used as a definition. There are several other equivalent definitions, but I can kind of commute this sum over F with the intersection. So then, but this intersection, or the finite sum of generator and the K, this is just by definition what was K prime F. So that was a pullback. Now these two things are sub-objects in the big direct sum. So this pullback actually defines just the intersection. So this will be direct sum over, sorry, the sum over F, K F prime. So then, when I have this formula, I can compute phi of the k. So that's the phi of the sum of the k primes with the f, so sum over f. Now, just by, in any abelian category, I can compute the map and the sum. So this will be the sum of the phi of the k prime f. And this is, so this phi of the k prime f, this is precisely the image of the map, which is phi mu and lambda sub f. So, with this computation, the conclusion is that it is enough to show that these are all zero, right? If these are zero, then this is zero, the sum is zero, so the phi of k is just zero. So that's the first reduction. And the second reduction, I'm now using the G as a generator. So since G is the generator, instead of showing that this composition of three maps is zero, I'm going to show that the composition of the four maps is zero. So phi mu lambda sub f alpha. Well, so again, since G is the generator, again, it is enough to show that this composition of the four maps is zero for any alpha in the home G to the k prime. Right, so this is more or less the definition of a generator. Okay, so why this composition of the four maps is zero? Well, this is now just a computation. So take this phi mu lambda sub f alpha. Well, instead of writing this two maps mu and lambda f from this commutative square, right? So have this composition of the lambda f and mu. I'm going to use this composition. So keep phi. Now I have a sum over f um em mu prime alpha. So using this commutative square. So then, since the composition of the, by looking at the definition, the composition of the phi and um is just the f of m, I can rewrite this as the sum, again, or some finite set f, f of m, bm, mu prime alpha. And also, I can write this as a composition, so f take composition with the sum over f m bm mu prime alpha. That will be of course the same thing. But now in this formula, I can keep the f and look at the sum of the so what I have mpm.
I don't understand what has happened on the last step. So
On the last step, well, I kind of if I take this, well, look at the result. So if I take this composition, right? This is just a finite sum, right? So this will be the composition of the f and m. So this, since in this sum, this f is the same for every summon, I can just pull it out in the composition.
we consider M as a map from G to A.
Yes.
Right?
Yes.
And how we then take F?
Hmm?
How we apply F to the map which has a target in A?
No, that is because we have these diagrams too, right?
Yes.
So we think that this little m is the element in this module, which is a submodule here,
Yes.
but also there is a map f that makes a map from the G to the B.
Yes. So we in this formula we consider M as a map from G to A, right?
M, yes, M is a map from the G to A, yes.
And then we need to compose it with a map which is from A to something.
Well, where is the map from A? I'm not sure that I understand what you're talking about.
У нас маленькое оно из Ж в А бьет. То есть, если написать вот эту сумму, это отображение из Ж в А. Вот вся эта сумма. Потом мы применяем F.
Да, но, да, вся эта сумма, это отображение из конечной суммы G сюда.
Что значит скомпоновать вот с этим? Вот справа написано отображение морфизмов категорий, а мы его компонуем с морфизмом модулей. Вот. В нижней строчке справа.
Yeah, so let's think about it. So the again, alpha is from the G to the K prime, so this whole sum is the this is the map from the G to the A, right?
Yes.
Yeah. So maybe instead of instead of writing the composition, I can write something that I apply this. Okay, I think now this makes sense.
But we don't know that this map lies in M. So not any map from G to A lies in M.
Well, maybe we can just verify this by a very specific map, right?
But we know that M lies in M, and it is a right module.
Yes. Yes.
So maybe if we multiply on the right, it still lies in
Yeah.
M.
Okay, so to finish the computation, take this formula and keep the f and rewrite what's inside. So inside f now I want the sum over f as before. Then I have psi um, em, mu prime alpha. Okay, so I'm just saying that again I'm using the definition for the map psi, and I know that the composition of the psi and um is just m. So I'm just plugging that formula here in this sum. Okay. Finally, the last step. So this is f applied to the composition of the psi mu alpha. Sorry, lambda psi f alpha. Okay. So this is because I can now look inside in this last step. I have this composition of the em and lambda prime. So again, this is the map in this limited square. I want to replace this by this map. So finally, the observation is of course that the composition of the mu and psi is zero, just by the definition of the mu, since this is a kernel. So this composition is equal to zero, hence this whole map is zero. And that's the end of the proof. Okay. Okay, so this kind of was the most complicated proof in this subsection, and now I just want to derive some observations from this. So maybe it's better if I just erase this proof, because I still want to keep this diagram, so diagram is important for editing. So there will be several corollaries. So corollary 1 is that from this lemma we can derive that the functor I is fully faithful. Well, the observation that this functor I, which is, let me repeat the definition, this is just a home in the category A from the G to something. So this is faithful because G is a generator. So it's faithful. Since G is a generator. So the non-trivial statement is now the fullness of this functor. Okay, so now in that diagram I want to take M to be just the whole home. So I'm still using the same diagram where there is some map F, but now just this horizontal map is just the identity. Okay. Now, if I continue to use this definition of the psi and the phi, and also maybe still look at this diagram from the proof of the lemma, well, first of all, I can notice that psi is an epimorphism, right? Again, this is because G is a generator. Well, since psi is an epimorphism, the image of psi is just A, so actually I can say that in this case phi factors through psi. So now if I take some map F, right, so that will be a map from the home from G to A to the home over A from G to B. Right. So on one hand, this is the map that we need in that diagram. On the other hand, when I want to show that this is a full functor, right, I want to show that any map like this, right, this is the map when I apply what's this F is in the home of the I of A to the I of B, right? So I want to show that any such F is actually can be lifted to a map from A to B. But this I can do, right? Because I know that psi factors through, so if I repeat this diagram, direct sum of the G, this is map psi to the A, this is map phi to the B. It factors, so there is map which I'm going to call F tilde. So from the A to the B. So in formulas, this means that the composition of the F tilde psi is the same as phi. But that's exactly what is saying that the home over A, G, G F tilde is equal to F. This is the last observation, kind of tautological, but it's kind of using again these definitions of the psi and phi. But that's the end of the proof, right? Since I know that now in this case phi factors through the psi, there is this map F tilde, and this F tilde from A to B is exactly the map such that I sends this map to the given map F. To understand why, for example, this formula follows from this commutative triangle, you just need to look back at the definition of what are maps psi and phi. Okay, so this is the first corollary. Now the second corollary, which is again derived by looking at the same diagram, but choosing the data a little bit differently. I want to show that I preserves injective objects. Preserves injectives. So, in the proof, so we let object B, let B be show that I want factor I to be, I'll get an injective object. Well, first of all, the observation is that if I look at the same diagram, I can write something like this. I have 0, k, direct sum of the g taken over m, then there is an image of psi, so this short exact sequence like this. Now, for the object B, I have a map phi, and by the lemma, right, I know that I can find the factorization of factorization. What's called extension? No. Lift. So maybe find the lift to the image. Right. So this exists by the lemma, and then I have another short exact sequence. I have the image of psi. This is embedded into the A, and then there's a quotient which is by definition the kernel of psi. Right, and
what is M here?
M?
M.
Well, at the moment I think I can just take any M, right? I didn't use any specifics about the M. Any M.
Okay.
Yeah. So I'm just trying to understand what it means that I have object P which is injective. I kind of have some additional properties in this case, right? So this exists in general by the lemma. Now I take this B, there is a map here, and then since B is injective, there is an extension. So the conclusion is that in the case when B is injective, again, I can say that phi factors through psi as before, right? So on the previous step we obtained this by some specific choosing M. In this case M is anything, but B is injective, but we still by this injectivity get the same conclusion. Okay. Now I want to be a little bit more specific. So I want to take object A to be the generator. So A is equal to the generator. So now we can notice that in this diagram, maybe I now rewrite this diagram. So I have M, which is submodule in the home from G to G, but this is just the ring R. So in this case, M is just the right ideal, and there is a map F to the home G. In other words, factor I applied to the okay. Maybe I'll finally erase this part. So, for any map like this, right? So there is still there are no restrictions on the f, right? So for any f, which is a map from this ideal M to the I of B, right? There is map, say, f prime, so there is map f prime from the G to the B such that f is equal to the I so I of the f prime. So here I'm using exactly the same argument as at the end of the proof of the previous lemma. So that's the same thing, but notice that in this case G is equal to A, right? So such that F is I. So what it means is, going back to this diagram, I have a 0 ideal M embedded into the ring R. So then there is a map, any map F from the I applied to the B, and then I claim that there is this extension F prime. But that's all we need to show by the Bayes criterion. So I show that I can extend the map to the object from any ideal to the ring, right? So by Bayes criterion, I of B is injective, and that's the end of the proof. So we proved two important things, that this functor I is fully faithful and that I preserves injective. So the next, I'm going to call this maybe corollary 3, but this is just a general categorical property that the Q is exact. This doesn't rely on this computations with the diagram. It just relies on the fact that if you have two adjoint functors, maybe a little proof of this, so the situation where I have adjoint functors Q and I, like this. So Q is left adjoint to the I. So the left adjoint is exact if and only if the right adjoint preserves the injectives. That's just a general statement about the abelian categories. And why this works? Well, you can take, say, a short exact sequence, ABC, short exact sequence. Since Q is left adjoint, so Q is automatically right exact. Is right exact as left adjoint. So I can apply this Q to this short exact sequence, and I'll get a sequence with 4 terms. So potentially I have some kernel, let me call this K. Then this is mapped to the Q of A, Q of B, Q of C, right? It's exact on the right, but on the left, the potential there will be some other K, right? I want to show that this K is actually 0 for any short exact sequence ABC, right? That would be enough to show that the corollary 3 is true. Okay. Now, if I take any injective object, so say I is injective, since the home into I is an exact functor, I can write that I have a 4-term sequence with the homes. Wait, so this I take a functor into the I, right? So it's a contravariant functor. So this will be Q of C I mapped to the home Q of B I mapped to the home Q of A I, and finally there will be home from the K to the I, and then 0. Okay? By the exactness, home into the injective object. Now I can use the adjunction, right? So I can write this as the home C and I applied to the object I. This will be the home B I object I, and finally this is also home A I of object I. Okay? But I of the object large I is still injective by corollary number 2. Right? So little I preserves the injective. But if this is the case, it means that when I apply home into the I of I to the short exact sequence, I still get a short exact sequence, right? So this thing is a short exact sequence. But if this is a short exact sequence, it means that the home, so finally the conclusion is that the home from k to the I is 0, and that is true for any injective object, right? But this implies that the k is equal to 0, right? Because we have a Grothendieck category, any object can be embedded into some injective object, so in particular that map has to be non-zero, and for any injective we know this form is 0, so that's a contradiction unless k is equal to 0. So parallelity is just a general categorical observation that doesn't really depend on anything that I said before. Okay. So finally, I don't even want to formulate this as the independent lemma. I can do the following computation. If I look at the home composition of the Q and I, some object A, to some object B, so by the adjunction, I can write this as a home I of A, I of B, and since I know that I is fully faithful, I can write this as the home. So this was in the category A, this was in the R. Now this is home over R between A and B. Right, so last step is because of the corollary one, I is fully faithful. But now we can apply the Ioannidis lemma, right? So this is for any A and B. So applying Ioannidis lemma, we get the conclusion that composition of the two functors Q and I of A is again A, and that is for any A in the European category. So,
the indices and R are wrong. So I and B are.
yeah. So this is in the A, this is in the R, and this is in the A. So if we summarize all the discussion, we have the following, maybe theorem, which is what is called the Gabriel theorem. I think this is from 1964, but the thing I'm doing on this lecture is not there, of course, the original proof of the Gabriel and Popescu. There is a very short paper, maybe just 2 pages long, by Barry Mitchell, which is called the elementary proof of the Gabriel-Popescu theorem. This is the proof I'm doing today. And this paper is from the early 80s, I think. So, in this situation that I don't want to repeat all the assumptions, so I have a Grothendieck category, I have a generator, and the morphism ring I denoted R. So the conclusion is that the A is equivalent as the category to the category of the R modules modulo some subcategory T. So where T is just the kernel of Q. So, as a remark, we can notice that the T is localizing subcategory. So the thing to notice here, of course, I have a quotient of the categories, but this is quotient of the abelian categories. Right, so it's not something that I explain in this course, but I kind of hope that you know that there's a notion of the quotient in the Serre quotient for abelian categories. You can take an abelian category, and inside this abelian category you can take a Serre category. Right, Serre category means that whenever we have an extension ABC, the middle term is in this subcategory, if and only if the terms A and C are in this subcategory. That's the definition of a Serre subcategory. And localizing subcategory means that this Serre subcategory also closed under coproducts. Some additional property, which is kind of useful in many applications. Well, for example, if the subcategory is localizing, it means that the canonical functor, say in this case from the R modules to the quotient A, has the right adjoint. So here I'm kind of relying on your knowledge of abelian categories a little bit more than in the other places of the course. So anyway, so the upshot is that any Grothendieck category is in fact can be presented just as a quotient of some module category.
So is the converse true that quotient of category of modules by some subcategory is the Grothendieck category?
Yeah, I think it's true. Well, it's, yeah, I think it requires some verification. It's not clear, for example, why the equal limits will be exact, but I think this is true. Now, of course, notice that the homological properties of the R modules and the A could be different, right? For example, in the R modules, we always have enough projectives. When we take a quotient, it's not necessarily true that we have enough projectives. So, but at least that's what we have, and this is the observation that I'm going to use to show that in the derived category of a Grothendieck category, every complex has an K-injective resolution. Okay, so let's finish this Gabriel-Popescu theorem and return back to the K-injective resolutions in the derived category. So it looks like that probably I wrote my notes on 2 different days, and now I think I changed notation. So I have, as before, these categories of R modules, right? So then there is the quotient functor Q to the category A, and I think before the right adjoint was called I, right? But now I changed my notation and call this little I. Sorry, I call this S. So this right adjoint is now called S. Sorry. It's just a little bit more natural for me to call this S and Q than Q and I. Well, because S is kind of like a section for the functor Q. So S was equal to I before. Sorry for this switch of notations, but if I continue to use I, I'm probably going to make some mistakes. So first of all, we can extend this more or less by trivial reasons to the homotopy categories. We have a homotopy category of the ring R. So this is homotopy category of the abelian category of the right R modules, but for the shortness of the notation, we're going to write this as the K of. So then there is a homotopy category of A. So then we can automatically extend these functors. I'm going to call this K of Q and also K of S. Right? This is just a general observation. Whenever you have 2 abelian categories, you have functor within abelian categories, you automatically can extend this to the homotopy categories, just applying this to each term in the complex. So what's actually hard is to extend this to the derived categories, and to do this you need derived functors. But you can also notice that in this case, right, since we know that the Q is exact, and being an exact functor means exactly this preserves the acyclic complexes, it is automatically determines the functor on the derived categories, right? So since in our situation Q is exact, we have a functor. I'm going to call this d of Q from the derived category of the ring to the derived category of the category A. But this d of Q is the same thing as the left derived functor, or the same thing as the right derived functor of the Q. When exact functor, this is just the same. Or I as well can just call this functor Q, but to indicate that this is act in the derived category, I call this d of Q. So now I fix notation. So L sub A, this will be by definition the kernel of the d of Q. So that is just some triangulated subcategory inside the D of R. Okay. So let's prove some properties of this subcategory L of A. Well, the claim is that the derived category of the Grothendieck category A is equivalent to the right orthogonal to this L sub A. And also, there is a second claim, which is actually more important. There is a set of objects. Let me call this L with a different font, such that L sub A is the localizing subcategory kind of generated by this set of objects L. Okay. So the proof is kind of two steps. Well, in the first step, I can, well, actually two more or less independent steps, because these two statements are more or less independent. So step one is to show that the derived category of A is equivalent to the quotient of the derived category of the ring R by the L sub A. Okay, so, and notice that, well, if you prove this, we more or less immediately get the statement in the proposition, this one. Okay, but to show this is, so the plan is to show, so we show that the derived category D of A has the universal property of the quotient. And now, since the quotient is unique, we'll get this equivalence of two categories. Okay, so let's take a functor f, which is a functor from the derived category of the Grothendieck category A to some other triangulated category S. So f is a triangulated functor, and of course I assume that S is some triangulated category. And I want to assume, of course, that the L sub A is contained in the kernel of this function. So I have two diagrams from which I can see what I need to show. I have the homotopy category of the ring R. So then there is a functor QR to the derived category of the ring R. So then, sorry, this functor F is not from the derived category of A. This is from derived category of R, of course. Okay, so yeah, so then I can write this functor F, which is a functor to the S. Here there is a functor which I denoted Q, K applied to the Q, to the homotopy category of the abelian category A. Okay, and since this Q on the abelian category, this was the quotient functor, the K of Q is also a quotient functor. And so this category, this triangulate category is the quotient of this triangulate category. Hence, if I look at this composition, I can say that there is a unique functor. So there is a unique functor which I'm going to call F, maybe with a bar. Well,
Why it is a quotient?
because the Q itself is a quotient.
Yes.
So, and also, well,
So we assume that Papescu's theorem holds true, or we are proving it.
no, we already proved it. It's just the result of all the previous
yes.
discussions.
So
we prove this, and they then kind of look at the same thing, and take the homotopy category of the left and on the right.
yes.
So, but then it's I think it's quite easy to see that this functor is again a quotient functor.
So it's just a corollary of this theorem.
Yeah, so you can even explicitly write this k of A as the quotient of the k of R modulo k of T, of the homotopy category of all the modules which are contained in the T. Okay, so why we have this unique functor f bar? Well, that is because we have another commutative square, and the trivial one. We have a homotopy category of the ring, homotopy category of the category A. So here the functor k of q is acting. Then there is a quotient functor q r. There is a quotient functor q a to the derived categories of the ring and of the A respectively. And here the functor is g of q. So by looking at this diagram, we can see that if I apply quotient functor qr to the kernel of the k of q, right? So this is contained in the kernel of the d of q, which is L sub a by definition. So by using the universal property of this quotient, now I can claim that there is a unique functor f with a bar. Okay, now, yeah, so the problem is that we only define this functor on the homotopy category, and of course we want to define this functor on the derived category of A, right? To say that the DA has the universal property. To do this, I take an acyclic object, so let B be an object in the homotopy category. So is acyclic object. So using formulas, I can just simply say that the QA of B is 0. Okay. I can also notice that if I have this identity for the functors Q and S such that the composition is 0, the same will be true if I apply this to the homotopy versions, right? Because we just apply this drawers on each complex, so it's clearly true. So then I take this identity and take a composition with the QA. So then QA is equal to the QA, K of Q, K of S. And using that commutative square, I can also, right, instead of the composition of the K of Q and QA, write this as follows. So this will be the D of Q, Q sub R, K of S, right? Using commutativity of that.
What we are proving? We are proving step 1, right?
Yes. What I want to show that G of A has the same universal property as the quotient.
Yes.
So what is your S?
S is just some triangulate category.
Oh, okay.
So
here you think S is right and strong.
Yeah, so you're right. Well, maybe this is not a good notation, so maybe let's call this triangulate category T. Okay, but at the moment I'm just trying to do some computation with an acyclic object. So I have this identity kind of for trivial reasons, and so since if I take a cyclic object P, if I apply this left hand side and right hand side of this identity, I get 0. So the conclusion is that d of q, q sub r, k of s, everything applied to the cyclic object B is 0. So this composition is 0. So since this, now I can look at the object which is just q sub r, k of s, applied to the acyclic object B, right? So I know that I get some object here, where if I apply d of q to this object, I'll get 0. What it means for the cohomology of that complex. Again, so this functor q is just applied kind of term-wise. This is an exact functor. It preserves the cohomology, right? So I want to say that this complex has cohomology in the subcategory T, and since this is killed by the functor q, so it's in the kernel of q. Okay, so if I try to compute functor that I constructed by that argument, so f with a bar on some acyclic complex B, I can rewrite this as follows. First, I can kind of plug in the identity, so k of q, k of s, which is just identity, still applied to the B. Now, using the diagram, which I used, this one, so I can rewrite this as the f q of r, k of s. Again, everything is applied to the B. So let's check this. So k of s can keep instead of composition of the f bar and kq. So instead of composition of these two functors, I use the composition of these two. And when I do this, I'll get an object QRKS of B, which has cohomology in T. Now, what's the observation? So observation is if I take Q sub R K of S, which is applied to the B, so this will be in the L of A, right? In the kernel of the D of Q, which is just follows from this previous identity. And the L of A is contained in the kernel of F. Well, because I consider factor F with this property. So, so the conclusion is that if I compute F bar on the object B, I'll get something quasi-isomorphic to 0. Right? Because if I compute F bar on the B, I need to apply F to this thing, but this thing, Q sub R K of SB, this is in the kernel of F, right? So when I apply F to this, to do this thing, I'll get 0. So it means that in fact factor F with the bar that I constructed is maps acyclic complexes to acyclic complexes, right? This was any acyclic complex. So the conclusion is that there is a unique functor F with the 2 bars, which will be a functor from the homotopy category of A, modulo of the acyclic complexes of A, which is of course the same thing as the D of A, to the now category T. Right? And hence we have this step 1. So that's the end of the proof of the step 1. I checked that the G of A has the same universal property as the G of R modulo L sub A. Okay. Okay, so this is the step 1. Now I want to go to the step 2. Erase it and just. So step 2. So in the step 2 I want to show that L sub A, which was defined as the kernel of the DQ, is actually some localizing envelope of a set of L. And I will give you specifically this set L. So proof of this. Well, I don't want to write proof for this independent step. So this is the proof of the step 2. Okay, so this will be again some kind of argument that uses some set theory, but a little bit more elementary than before. So let me take B to be the cardinal, which is the maximal cardinal of the cardinality of R, and also now I have a problem. I'm not sure how to write Aleph 0. So this is supposed to be Aleph 0. I'm not sure how to do this on Prisma. So this is the best I can do. So now let me give a definition of the set L. So L is defined to be all the objects E, which are the complexes of the ring R, such that, well, Ej is equal to 0 for J positive, then A0 is the same as the ring, and for the negative J I have the following. So Ej is equal to the direct sum of the copies of the ring R over the set I sub J. So where the condition is that the cardinality of the set I sub J is less or equal than beta. So this is for J negative, and also the condition, additional condition, is that if I apply the Q to the cohomology of this complex, I'll get 0. So this is for any I, any integer I. Well, of course, this is only interesting for the negative integers. So that's the definition of the set L. So now the claim is the smallest localizing subcategory containing this set L is precisely L sub A. So let me say that we want to show that the L sub A is equal to the log L with this specific L. Okay, so let's take some M object in the L sub A. Right, so for this object,
I don't understand why we consider complexes of consisting of R in the category A.
no, L sub A is a translate subcategory in the D of R.
Oh, yes.
Yeah. So take an object in the L sub A, all right, and then you have a distinguished triangle. So then there is a distinguished triangle. So like this, M0, M prime, and then I just repeat everything with a shift. So where M0 is in the log of L and M prime is in the log of L right orthogonal. Right. So why this distinguished triangle exists? Well, that is because we now work in the derived category of the ring, right? And we proved last time that if you take a localizing subcategory generated by an object, then we have such triangle, right? So the only problem here is that our subcategory is not generated by an object but by a set of objects. But this is not really a big deal, right? Because whenever localizing subcategory is generated by an object, right? Generated by a set of objects, you can just take the direct sum of all the objects in the set, right? So it exists since this is a set, right? And maybe let me write this as a why this is true, because I can, for example, introduce maybe t. I don't use t, so this is just a direct sum of all the, say, p in the L, right? And then the localizing subcategory containing L is the same as localizing subcategory containing G. So actually saying that I have a set of generators and I have just one generator is the same thing, right? Clearly this is the same thing, right? Because for example, if I have an element, for example, I want to show that every element from the set L is here, right? Since the direct sum is here, every direct summand is here, because this is localizing subcategory, it is closed under direct summands, right? And if Y, for example, G is here, well, because, well, this is localizing closed under direct sum, so it can, so not GT, sorry. So this is generator T, right? So these two things are the same. So the arguments of the previous lecture can be applied to this situation also, and we can claim that there is such distinguished triangle. Yeah, it also looks like it's time for a break. Maybe let's take a break before I've done anything serious in this step.
Мы когда доказали первый шаг, мы доказали тем самым, что ДА это ортогонально.
На самом деле, да, потому что, ну, как? Логика такая, что у нас есть это утверждение, что мы доказали в шаге 1, да?
Да.
А теперь мы докажем еще вот это свойство в шаге 2, да? Но тогда это будет означать, что, ну, плюс вот эти замечания, которые я использовал, это будет означать, что LA порождено каким-то одним объектом.
Да, да.
Значит, это как раз означает, что мы как бы в ситуации локализации Босфилда, да? Ну, помните, у нас был лемма с 6 эквивалентными условиями. Я говорю, что эти условия выполняются, когда эти условия выполняются, это называется локализация Босфилда.
Да, да.
Ну, как бы лемму сформулировали, используя там условие номер 6, условие номер 1, реальности когда условие номер 6, но одно из условий, ну, 3 и 4 означает как раз, что фактор категории эквивалентно правому ортогоналу. Так что вот это утверждение про то, что производная категория это правый ортогонал, производная категория А это правый ортогонал LA, оно будет как бы следовать из шага 1, шага 2 и той леммы 6 пунктами. Как понятно, моя логика?
Да.
Хорошо.
Да, нашел третье условие в той теореме
Да.
означает. А мы, получается, какое условие из этой теоремы доказали просто? Кажется, что...
В какой момент?
Ну, вот когда докажем шаг 1 и шаг 2.
Ну, смотрите, есть тривиальное замечание, что быть порожденным множеством объектом, быть порожденным одним
Да.
объектом, это более-менее одно и
Да.
то же. Значит, соответственно, у нас получается ситуация, когда вот есть производная категория кольца, внутри нее есть подкатегория LA.
Да.
Она по факту порождена одним объектом.
Да.
То есть, если мы вот шаг 2 докажем, то мы попадаем в условия того утверждения, которое мы доказали в конце предыдущей лекции.
Да.
Ну, там условия, формулировки были использованы условно разделились, но в реальности мы доказали условия разделились.
Да.
Вот. Ну, а как бы утверждение, которое мы сейчас доказываем, это, как говорится, утверждение номер 3.
Да. Утверждение, да, с прошлой лекции, оно даст, что это ЛА это ядро какой-то локализации.
Да.
Это условие
Один.
1. Да.
Да. Значит, у нас на самом деле, да, если мы рассматриваем как бы под категорию внутри производной категории кольца, ну, локализующую категорию, порожденную там множеством объектов, да, то тогда вот эти все 6 условий выполнены.
Да.
Ну, вот, в частности, условие 3, что дает вот эту теорему, потом что доказать.
Можно еще вопрос, вот я не понял доказательства такого факта.
Если есть категория Grothendieck, то Калим совпадает с Калимом. То есть как вот это? Здесь буквально три строчки.
По полиции совпадает с Калимом.
Да. Это здесь доказательство было буквально три строчки. Мы использовали вот эту лему.
Это просто это самое общее такое
Да.
наблюдение.
Как это получилось? То есть мы...
Сейчас у вас здесь какой по полиции? Я просто не помню в контексте.
Там Калим был тотальный конкуренц.
Ага. Да, значит, это на самом деле, ну, в реальности это не было доказано,
Да.
потому что я сказал следующее слово. Помните, у нас был комплекс гомологический, когомологический комплекс
Да.
Руса, и из него мы увидели, что гомология совпадает с производными функторами.
Да.
Здесь, грубо говоря, просто дуализируете все это доказательство, то есть
Да.
переходите к исполненной категории. У вас будет гомологический комплекс Руса,
Да.
и его гомологии совпадут с левыми производными функторами такого предела.
Да.
Ну, соответственно, как бы, если у нас, например, категория Grothendieck, у нас никаких левых производных функторов к Калиму нет, ну, старше,
Да.
есть только нулевой. По этой причине Колим и Лин просто совпадают.
То есть, не понял, то есть предположим, мы доказали, что, то есть точно доказали, что если посчитать вот этот комплекс Руса,
Да.
тотально, оно для доказания двойственного утверждения,
Да.
здесь когомологически, мы доказали,
Да.
что
Что я понимаю.
Калим это гомология тотально.
Да, ну, двойственное утверждение, которое мы доказали, это что вы берете когомологический комплекс Руса, его когомологии, это производный функтор от Лима. Соответственно, двойственное утверждение, которое мы сейчас используем, берете когомологический комплекс Руса.
Вот я не понял тогда, то есть у нас, я помню, что мы доказали, что Калим, если взяли какой-то Ж, построили когомологический комплекс Руса, то его производные функторы Калим, производные функторы Лима, то есть Калима, они равны когомологиям этого комплекса Руса. Это мы доказали.
Да.
А как это связано с Хо Калима? Или с Калимом? Вот эти производные функторы связаны с тотальным комплексом. Как тут переход осуществился?
Нет, ну вот у вас есть как бы вот этот самый
Холлинг,
Да.
Это некоторый комплекс.
Да.
У него нет никаких технологий, кроме люд.
Да, как это?
Потому что какие у него космологии? У него космологии требуют производные Холлингу.
Да, вот это как увидеть.
Это следует из того, что мы сделали для них. Просто это двойственное утверждение.
Да, а для лимов это как получается? То есть мы...
Для львов у нас был какой-то аргумент, мы там тему Grothendieck использовали, все такое.
Да, но это будет для комплекса Руса. То есть это тотальный комплекс, это и есть тот комплекс, который мы построили.
Да. Ну, там просто, когда мы это доказывали, мы доказывали для одной категории, там просто не было тотализации, потому что там просто комплекс был.
А здесь просто добавилось из-за того, что мы вот сюда, здесь в ЦА, из-за этого добавилась тотализация.
Да.
То есть это, по сути, то же самое.
Да.
И поэтому, да, здесь Хокалин.
Да. Ну, просто, грубо говоря, у вас здесь получается говорить чуть сложнее, потому что там, у вас получается как бы не комплекс, а бикомплекс, у нее есть тотализация, но, в общем-то, более-менее те же самые аргументы вы доказываете, что у этого комплекса, да, у него есть космологии, и эти космологии как раз совпадают с новыми производными функциями
Да.
для Холлинга.
Да, и мы, получается, знаем теперь, что нет производной функции в категории Grothendieck.
Да.
Поэтому у Калима вот они к гомологии только в нулевой степени.
Да, и такой настоящий обычный Холлинг. Это диаграмма, да.
Да, настоящий. Это из того, что мы для Лима мы это все проделали.
Да, для Холлинга, соответственно, управление.
Да. Только вот для Лима, например, я не очень понимаю, мы написали комплекс Руса.
Угу.
Дальше мы доказали, что его гомология это производная функция.
Угу.
Как это связано с Холлингом?
С Холлингом?
Да.
Холлинг.
То есть Холлинг определяли как какое-то, соответственно, ядро какого-то отображения. То есть как это связано с комплексом?
Мы не определяли никак ядро, мы определяли, если хотите, там, правильно сказать, геометрический зоид, но называется геометрический
Ну,
зоид.
доставили, да.
Да, довольно треугольника.
Да.
Да, здесь просто нет, здесь ситуация такая, что у нас есть, с одной стороны, теория triangулярной категории,
Да.
и там у вас есть только вот эти геометрические пределы по пределу для очень простых диаграмм.
Да.
А потом я это делал расширяю, и когда у меня производная категория, я могу определить геометрические пределы по пределам для производных диаграмм.
Да.
Теперь, соответственно, если вопрос про то, как связано, для, соответственно, как определяется геометрический предел для производной диаграммы.
Это вот даже для обычной диаграммы, когда n определили для натуральных чисел. Там вот получается у нас есть одно определение, это через строение довыделенного треугольника.
Да.
А второе это через производные функторы.
Да, второе, это можно
Через
брать,
комплекс Руса.
можно брать комплекс Руса, да, и можно считать его, ну там что-то получится, можно считать его как аналогии, да.
Почему одно и то же получается даже для этого?
Потому что, ну, то, что получается одно и то же, совершенно не очевидно. То, что вам на самом деле надо лучше сделать, это следующее. Если у вас простая диаграмма, вы интересуетесь у этой простой диаграммы геометрическим, например, пределом. Да?
Да.
У вас есть вот это определение из определенных категорий, но у вас еще есть такой способ, просто по этой диаграмме строить комплекс Миллера. Помните, когда я объяснял, просто в самом начале был комплекс Миллера.
Да.
Можно доказать, что комплекс Миллера, так это комплекс из двух членов, у него есть только нулевые и первые космологии. Да? Можно доказать, что они совпадают как бы с Лимом и Пиролингом. А доказательство ровно такое, что это комплекс Руса.
А мы не доказали, получается, что Холлин и гомологии комплекса Руса совпадают. Или это из чего-то следует?
Холлин, гомологии комплекса Руса.
Да.
Для простых диаграмм, да?
Да, вот для натуральных чисел.
Да. Это следует по такой логике, что вы можете, если у вас простая диаграмма, вы можете считать для нее, грубо говоря, тремя способами. Через комплекс Миллера, через комплекс Руса, ну, комплекс Миллера и Руса, очень говоря, разные будут все-таки, и при помощи вот этого выдного треугольника.
Но в комплексе Миллера там критерии как бы нет поль старше двух,
Да.
но они в принципе есть.
Ну, для простой диаграммы нет.
И вообще никогда.
Никогда.
То есть ни в какой категории. То есть не важно, Grothendieck она или Grothendieck выбор.
Ну, где существует выбор,
Да.
да. Да. Насколько я понимаю, правильно. Если у вас как бы диаграмма пробежала ранним часом, то у вас старших пределов нет.
Да.
Есть только нулевой метод. Да. Да, я тоже еще пытаюсь сказать, что если у вас простая диаграмма, как бы, например, в категории комплекции, да, то у вас есть как бы три способа посчитать для нее геометрический предел, да, при помощи общей теории треугольных категорий, там некоторый треугольник, может при помощи комплекса Руссо, может при помощи, соответственно, комплекса Миллера, да. Вот, и все три ответа это одно и то же.
Да.
Но чтобы увидеть, что это одно и то же, нужно, что на комплекс Руссо внимательно посмотреть.
Ну, надо использовать доказательство комплекса Руссо, то, что оно совпадает, ну, что его гомологии совпадают с производными римами. Да? Для комплекса Миллера вы просто, грубо говоря, повторяете аргумент. То есть вы не сравниваете комплекс Миллера и комплекс Руссо, вы делаете вид, что вы не знаете, что существует комплекс Руссо, берете комплекс Миллера и просто делаете для него такой же аргумент.
Да, ну, у Вайгеля такое что-то для категории модулей, где, когда доказывал универсаль, что это универсальный дельта функция.
Да, ну, в общем, можно как бы забыть на комплекс Руссо,
Да,
просто
отдельно сделать. А потом, и как это связать с триангулированной стороной?
Вот, это триангулярной стороной, то, что вы берете, как бы, у вас будет какая ситуация, у вас будет, грубо говоря, морфизм между прямой произведение, да, если прямое произведение. Вы достраиваете это дело, там, ну, конус какой-то берете, грубо говоря.
Да.
У этого конуса есть там космология.
Да.
У него есть нулевые первые космологии, которые в точности такие же, как, соответственно, космологии в комплексе Миллера. Но потому что на самом деле это просто более-менее одно и то же.
Да.
Вот. Поэтому у вас более-менее по определению геометрического предела для простых диаграмм определенных категорий совпадает с космологиями комплекса Миллера. А дальше вы проверяете, что новый комплекс Миллера совпадает с производными пределами.
Ну да.
Да, нам хочется все-таки не космологии проверить, нам хочется проверить, как бы получить изоморфизм производной категории в один изоморфизм. Что у нас тотализация комплекса, ну, у нас есть комплекс тотализация комплекса Руссо. И мы хотим понять, что это как бы конус. Ну, является геометрическим пределом. То есть просто видимо.
Можно, да, но как-то сделать, я просто про это не думал.
А в общем случае, когда нет комплекса Миллера, там что делать?
Это, наверное, правильно. Но надо подумать, как доказывать. Я из того, что я сказал, по-моему, не следует.
Ну, мне кажется, тут простая диаграмма, поэтому комплекс Руссо как-то просто должен быть устроен, и там руками, наверное, можно все проверить.
В смысле, мы руками понимаем, что комплекс Руссо квазиизоморфен этому
Ну да.
третьему члену треугольника.
И наверняка там просто геометрические эквивалентности.
Ну,
Геометрическая категория.
Я думаю, это правда, но просто как тот шаг, который я пытался на лекциях избежать, что-то не хотел проверять.
И эту теорему, получается, мы так, типа, намек на доказательство, то есть такого полного, не следует полное доказательство. И даже если принять, что комплекс Руссо и считать то же самое, гомологически и тотализированный, то же самое, что по колену.
Нет, мне кажется, нужно вполне себе
То есть следует.
Нет, но я не говорю, что это просто более-менее косвенное наблюдение к тому, что мы делали для комплекса Руссо, гомологического.
А тут важно, что нету старших гомологий, это только
Да.
нулевые.
Да, то есть, что у вас, с одной стороны, есть комплекс Руссо гомологический, у него есть только нулевые гомологии совпадают с кулином,
Да.
и поэтому это утверждение имеет смысл.
И из-за вот, здесь мы тоже доказывали, что если есть два функтора, которые сохраняют произведение, и на абельной категории равны, то тогда они
Да,
равны. Это здесь получается важно, что у нас только нулевые категории.
да, конечно. То есть,
Поэтому здесь на набелевой категории можно.
Да.
То есть мы знаем, что набелевые категории не равны.
Да. Мы знаем, что набелевые категории не равны, и это двойственно к тому, что было сказано для Алексея ранее.
Да.
Да. А после этого продолжаем как бы триангулируем, и они, значит, тоже обязаны быть там равны.
Да.
Потому что я могу сказать про произведение, ну, как бы по линии не надо продолжать, потому что он точно, просто будет останется, а по линии продолжаются как бы тем способом, что вы берете капитализацию уже этого комплекса Руси.
Да.
Да.
И здесь получается важно, что чтобы проверить, что применить эту лему, нам нужно знать, что они на набелевой категории, что Калин посчитанный на набелевой категории попадают в Абелеву.
Да. Ну, это понятно, почему. То есть,
Вы как раз из-за того, что нет.
да, да.
Спасибо.
Okay, so going back to the proof of this step 2. So I have this distinguished triangle that exists by the general argument that we told before. Lemma is 6 equivalent points. Now I also want to notice a trivial observation that if you take log of L, right, then this is clearly contained in the L of A, L sub A, right? Well, that is because we have this condition that Q applied to the cohomology is 0, right? So this will be in the kernel of the function Q. So log L is in the kernel of the function Q. So this means, since we know that M0 is in the log L, it is also in the L sub A. And so maybe let me write that this implies that the M0 is in the L sub A, right? So then also M is in the L sub A, it is given, right? So hence, since this is distinguished triangle, we can make a conclusion that the M prime is in the L sub A. So all the three objects are in the L sub A. Okay. Okay, so now what I want to show again now kind of the next goal. So the goal is to show that M prime is a cyclic complex in the category A. Right? If this is an acyclic complex, it means that kind of in the derived category, this is isomorphic to 0, right? So it means that in derived category, this is an isomorphism. So any object M from the L sub A will be isomorphic to an object M0, which is in the log L. This is what we want to show, right? So really the goal is to show that this M prime is acyclic. So let's suppose by contradiction that this is not acyclic and derive something that contradicts the something in this statement. So suppose by contradiction that M prime is not acyclic. So without possible generality, I can assume that for shortness I'm going to call this H, but this is just the zeros cohomology of the M prime. This is not zero. If this is not the case, I can translate and get this. So if this is the case, right, so this is M prime, and we agreed that M prime is in the LA, right? So since this is in the LA, or M prime is in the LA, we can conclude from this that Q applied to the H is equal to 0. Right? So this is in the LA was defined as the kernel of Q, so that this homology module Q has to be 0. So this means that this is the situation H is torsion, so this is the so we can take some common little h in the module H. Let's assume this is first not equal to 0, so we can generate a cyclic module. Well, we have right module, so let me write this as an HR. So we have HR, this is a right module, which is isomorphic, of course, by to the R modulo side, right? So that's a cyclic module that sits inside the H. So we have non-trivial, non-zero map of the modules. Okay, so, and also we can notice that the Q of the R modulo I is equal to 0, right? So since this is a sum module inside H, Q of H is 0, so the sum module Q is also 0. So then I have the following diagram. I can take the kind of the definition of the zeros homology. So I have the kernel of the D0. There is an epimorphism to the zeros homology of the M prime, and the kernel of this map is the image of the previous differential, so the image of the D minus 1. So then we have R modulo I, which is in a non-trivial way is mapped to the H0, so this is actually an embedding, right? And also, well, there is R, which is also mapped here, also there is an epimorphism. So we can combine this together, these two maps, so there is a map from the R to the zeros homology. Hence, since R is projective, there is a map to the kernel of the D0, and also ideal, which is in the right submodule in the R. Since if I look at this composition, I is mapped to the R, this is mapped to the kernel of the 0, this is mapped to the cohomology, this is 0. Actually, this factors through the image. So there is also a map like this. So we get the diagram using the essentially kind of trivial universal properties and the fact that R is projective. Okay. So now I want to construct a complex P, which will be an object in the set L. So to do this, I do this by induction. So I set P0 to be by definition R, right? So this is P0, this is R, and this is mapped to the kernel of the D0. And F0 will be, by definition, the following composition of two maps. So this will be, let me give this a name. So I'm going to call this maps G prime, and maybe G0. So then there is a map from the R to the kernel of D0, which I'm going to call G prime. And this is embedded, of course, into the M prime 0. So this will be a map from the P0 to the M prime 0. So inductively, we construct the complex in the map. So we have from the complex P to the complex M prime. So of course in the M prime, which we assume to be the kind of Oh, doesn't matter. So we do this by induction, and suppose we've done this for some index j, so let's do this for the index j minus 1. So to do this, it's kind of like constructing a resolution again. So we have some ej, which is mapped to the m prime with the index j. So here I'm going to need kernel of the differential, which is embedded into the module, and there's an image of the previous differential. So then I'll take the kernel of the differential. So this is differential in the complex P, which I assume that I have on the previous step. So this is map F with the index j that I already constructed. So then there will be a map between the kernels. And then again I take the pullback and I call the pullback Cj. So this is a pullback, and the map is going to be G with the index J. Okay, so we can notice that if we take the kernel of the differential on the complex P with the index J and take a quotient by the Cj that we just constructed. And so this will be something inside the cohomology with the index J of the complex M prime, which is more or less follows by the definition of the Cj. But since when I apply factor q to this cohomology, I'll get 0. If I apply q to the sub-object, I still get 0. So q of the kernel of the djp modulo cj, this is 0. Okay, so then the observation is that if I look at the cardinality of the cj,
why has the inclusion of cohomology in Bj into cohomology Hj of M prime?
well, because the cohomology, this will be, I'll have this pullback diagram, right? Then if the cohomology here, right, this will be the kernel of this map.
Yes.
And this quotient is the kernel of this map.
Yes. But we can see simply why it is injected.
Well, because whenever I have a pullback in any abelian category, then on the kernels, the map is a monomorphism. This is something that we used when we constructed resolutions.
And this big square is a pullback as well.
No, I'm taking pullback for this square.
Oh, yeah, yes.
Okay, so since we kind of have two monomorphisms here, so the cardinality of the C with the index j is less or equal than the cardinality of the P with the index j, and I assume by construction that this is less or equal than the fixed cardinality beta that we have in the beginning of the step 2. So then I can claim that there is a set. So I with the index j minus 1 such that the cardinality of this set is less or equal than the cardinality of the Cj, and there is an epimorphism. So there is an epimorphism from the direct sum of the ring over the set I with the index j minus 1 to the Cj. Okay, so then we can take this direct sum just to be by definition the object with the object. So next term on the left is the complex P that you're trying to construct. So this is by definition this direct sum. So then we have the commutative square like this. We have P with the index j minus 1. There is the, by construction, the epimorphism to the C with the index j. From the Cj there is a map to the image of the D with the index j minus 1. And then there is M prime j minus 1. So there is a map like this. Right? So the map from the Pj minus 1 to the M prime j minus 1 exists because this is projective, right? We have a, by construction, we have a map here, which is an epimorphism. We also have a map here on the image, right? So now using that this is an epimorphism, we can kind of lift this map from the projective to the M prime j minus 1. Okay. Maybe I'll try to squeeze the end of the proof on this blackboard. So also, so this is how I inductively define the terms in the complex. So I'm trying to construct this thing. So also I need the differential, right? And the, well, the map is this one, right? So this map that I constructed is the map F with the index j minus 1. So the only thing that is left is the differential. So the differential D with the index j minus 1 in the complex P. This is by definition the composition. So I have P j minus 1. I take an epimorphism to the C with the index j, and then the map from the C with the index j to the Pj. Right? So the image of this differential will be in the kernel of the next differential, so d squared is equal to 0. So anyway, so what we've done, I don't want to raise the, but maybe I can try to see it here. So what we've done, we constructed some non-trivial map, right? So the by construction, we can see that the P that we have is some object in the set L. Right? By carefully looking at what coordinates we have on each step, we can conclude that P is in the L. So then we have a map F, right, from the P to the M prime, and also the H0, zero is the homology of this F. So this will be map G that we started with here, right? So this is G which is not equal to 0. But this is contradicts to the fact that the M prime is in the right, or is in the right, yeah. So this is in the log L, right orthogonal. Right, so on one hand we know that the M prime is there, right? So all the such homes from the objects in the L to the M prime has to be trivial, right? But we constructed a non-trivial map because H0 this map is non-trivial. So that's a contradiction.
Why P lies in H?
Well, because we are construct this P by induction, right?
Yes, so my question is why oh yes.
So on the by definition of the P on the right from the 0, I have zeros.
Yes.
On the left, I do this inductively by this procedure that is displayed by several lines here somewhere on the blackboard. And also, I can notice that all the conditions that I have for the objects in the L are satisfied. The cardinality condition and also condition in the Q. So we constructed some non-zero map from some object in the L, and that contradicts the fact that M prime is in the right orthogonal to the log L. So this is a contradiction, and now we can say that the M prime is acyclic, so hence in this distinguished triangle this is something isomorphic to 0, this is a quasi-isomorphism, hence any element in the L L sub A is quasi-isomorphic to the M0, which lives in the log L. So this finishes the proof of the step 2. So I need to raise something here. Well, I just finally can say that if I combine steps 1 and steps 2, right, I can conclude what I want. So what was the original statement is that dA is equivalent to the right orthogonal of the LA, right? That is because, or maybe a little explanation why this is the case. Well, that is because we already know that we have the derived category of the ring. So then there is a quotient functor to the derived category of the ring modulo L sub A, right? We identified this already with the derived category of the A. But since now this L of A, L sub A, is the localizing category for one generator T that I introduced in the proof of the step 2. So this thing has the right adjoint functor, right? And then we just use this lemma with 6 equivalent conditions, right? So we have this right adjoint functor, or well, another way to say this, that there is distinguished triangle with a specific property. So another way to say the same thing is to say that this kernel L sub A is the, this localizing subcategory L sub A is the kernel of some localization. But anyways, the conclusion is that one of the 6 equivalent conditions that we proved before is precisely, I think condition 3, right, is precisely this condition. So hence this conclusion. And by the way, so that's the end of the proof of this proposition. So combining that general statement about 6 conditions, the previous computation for the derived category of the ring, Gabriel-Popescu theorem, and this computation, at this stage we already see, for example, that the derived category of a Grothendieck category have small homes, right? Because this is a subcategory, in particular this is a subcategory in the derived category of the ring, and in the derived category of any ring we already know that the homes are small, because this is equivalent, this derived category of the ring is equivalent to the homotopy category of K injective or K projective objects. And homes there are small. Okay, so we're almost done with this chapter. So let me just write one more diagram. So the same diagram actually that I already used. So there's a homotopy category of the ring. There is a quotient functor for the ring to the derived category of the ring. Then there is a K functor K of Q to the homotopy category of the A. And there is the quotient functor for the A to the derived category of the A. And then here this is D of Q, which is exactly the Q. So what we know about the right adjoint. So what we want to show, so again, the goal, it would be nice to show that the Q sub A has the right adjoint. Right, because if we have this right adjoint for the Q of A, what that means actually? I have this canonical quotient functor, and this quotient functor admits a right adjoint. What is the meaning of this from the point of view of resolutions? It means that for any object in the derived category, I have a K injective resolution, right? So this is equivalent to existence of a factorial K injective resolution. So why this is the reason why this is nice to have for such functor a right adjoint. But in this diagram, all other functors already have right adjoints, right? So, for example, for this one, why we have a right adjoint? Well, we proved this when we discussed K-injective resolutions, right? If the category is nice enough, for example, it has well, if we already proved that if you have a ring and we consider the right category of the ring, that any object has a K-projective and K-injective resolution. So here we have K-injective resolutions, hence there is a right adjoint functor here. And for the other two functors, K of Q and D of Q, also there are right adjoint functors. So functors Q sub R, K of Q, and D of Q have right adjoints. So the result, the existence of the right adjoint for the functor Q of A follow from just the general lemma. So suppose in the diagram just take a general diagram, so say T, D prime, and D. You can actually make this a little bit more general than the triangulate categories, but that's enough for what we do in this lecture. So I assume that I have 3 triangulate categories and 3 triangulate functors. Suppose that in the diagram, so Q, so this diagram, Q is a quotient functor. So in other words, this is a functor such that this D prime is the Grothendieck quotient of the T by some, say, fixed category, and this is just the canonical functor to the quotient. This is called the quotient functor. So also I want to assume that, well, and of course in this diagram, the G is just more or less the composition of this functor, which follows just from the cumulativity, and I want to assume that G admits the right adjoint. And G admits a right adjoint. Let's call this right adjoint I. So G has right adjoint I. So I is just a notation, so we can write it on this diagram. So I is right adjoint for the G. So then Q prime admits a right adjoint. Oh wait, sorry. Actually, I have a different notation, so let me change this very, very quickly. It's not really important, but I want to call this right adjoint K. To avoid mistakes, better to follow my own notation. So this is K, then Q prime admits the right adjoint I, and for this I, there is a formula. So I is just the composition of the Q and K. So Q prime admits right adjoint I, so it's somewhere here. And this I is the K and then Q. Okay, so this is just a general, kind of some general statement about the triangulate categories, which is actually quite easy to show. We will do this in a minute. But is it clear that if you have this lemma, if you believe in this lemma, then I have the conclusion, right? No, because in this diagram, we know that the 3 out of 4 functors have the right adjoints. I can take the composition of the 2, and they also have the right adjoint, which is composition of right adjoints. So if I have this lemma, I can conclude that the quotient functor Q sub A has the right adjoint, which is what I want, right? Because the existence of this right adjoint exactly means that the existence of K-injective resolutions. So really, to finish this whole theory, that in graph category of any Grothendieck category, any complex has k-injective resolution, well, I really need to prove just this lemma. This is more or less the last statement. So proof. So take any x which is in the kernel of Q and any y which is some object in the D. I can use the adjunction, write this as the home in the category D from the G of x to the y, but but this is 0, right? This is because if I want to compute the G of x from the diagram, I can see this is the same as the Q prime Q that I compute on x, but x is in the kernel of Q, so that's 0. For this reason, so thus, if I look at the home in the category T from the object x to the object y, so then I can identify of y, yes. That is because this functor, so what I'm doing here is just applying functor q on the homes, right? So I have such home, there's a canonical map to the home, which when I apply functor q, right? But I also claim that this functor q on the homes actually gives isomorphisms, right? And this is just follows by some general properties that I proved at the beginning of the course. Remember, when we discussed the right orthogonals, there was a general statement when you consider a kind of situation like this, where you have two objects, and but I claim that this is what happens here, right? So this is functor q, the whole functor. Now the second argument, the second argument of the home in this case is the k of y, right? But when I compute any home between x and the k of y, so x is in the kernel of q, right? So I'll get 0. So it means by this computation, maybe I should have said this before, by this computation, since this is 0, the image of the functor k is in the right orthogonal to the kernel of q. D prime is a quotient by the kernel of q, of course. So by that general theorem, if you take second argument in the home is in the right orthogonal in the category, then the quotient function uses an isomorphism on homes. So this is what we have. And now the rest is just simple computation by adjunction.
So we use here one of the lemmas that I've proved some lectures ago.
Yeah, so I think that was the lemma with 4 equivalent conditions. One condition was that the object is in the right orthogonal, second condition was that on the homes there is an equivalence, and the third condition was something about the root that represents the map, and the last condition was that the map is a section, something like this. So here we only use equivalence of condition 1. Okay, so now I want to take so any object, let me call this x, so this will be object x in the D prime, and y is as before in the D, and since q is a quotient function, I can always choose some other object x0 in the T such that q of the x0 is x. Well, just a purely formal observation, right? So since this is a quotient function, the objects are the same. Okay, so then home in the category D between q prime of x and y, Well, I can write this as a home, the same home in the D. I just plug in x0 in this formula. So this will be q0, q of the x0, y. Now I use the fact that this composition, G, composition of the q0, q prime and q has right adjoint k. So I can write this as the home in the category T from the x0 to the k applied to the y. And now I use this observation. So this will be home in the category D prime, q of the x0, q of the k of y. And finally, I again plug in the formula for the x. So this will be the home in the D prime, x I of y, right? So this is how we define I as a composition of the q and k. So that's the end of the proof, right? We proved that the right adjoint for the q prime is I. So finally, to summarize everything, so we proved the following theorem. So if A is a Grothendieck category, then quotient factor Q sub A from the homotopy category of A to the derived category of A admits a right adjoint right? But what's the result of a computation of this right adjoint on an object? That's exactly the k-injective resolution of an object. So in other words, any object of D of A has a k-injective resolution. So that was a long period we proved during a couple of lectures. Okay, so any questions about the previous demo or about this theory?
Why DQ has right adjoint? Why DQ has right adjoint?
Why? What? Why this function is right adjoint? Sorry, there's a very trivial reason why it has right adjoint. Yeah. So
Is the derived factor of S its right adjoint? So we have
yeah.
Z junction on the level of homotopic categories.
Yes. So yes, exactly.
So is it true if two functors are adjoint, then the derived functors are also adjoint?
Yeah, that's true. Mm-hmm. Okay. Yeah, and also we can conclude as the corollary from the theorem, but actually we proved this a little bit earlier, that in the derived category of a Grothendieck category, all the homes form sets, which is of course not true for any abelian category in derived specific logical examples, but the derived category homes are just some classes, not sets. From this theorem, you can just take two objects, since the derived category is equivalent to the homotopy category of the k-injectives, you just compute the homes as the honest maps in the homotopy category to k-injective objects. But also we proved this during the proof of the previous level that was before that. So, and sometimes this statement that the derived category is locally small, meaning that the Holmes form sets, is formulated as the existence theorem. So the people say that the derived category exists. So what they actually proved is that the derived category of the Grothendieck theory exists in a sense that this is locally small. Okay. So there are some other parameters that you can derive from the theorem, but I want to leave this as exercises in the next problem sheet. Okay, so that's the end of this discussion on the derived categories of Grothendieck categories. And the notice that when we do algebraic geometry, we can immediately know that we have k-injective resolutions, and all the functors that need to be right-derived, like direct image, home, or local home, they automatically have derived functors in the unbounded complexes. This is kind of the reasons why we need the general technique about Grothendieck categories. And the same can be also done, for example, for modules or for sheaves of, say, abelian groups, or sheaf of some R modules over topological spaces. Okay, so I want to start new chapter. So this is chapter 5. This will be the last chapter about homological algebra in this course, and this is a relatively short chapter. Probably I'm going to finish this next week. So this is compactly generated intermediate categories. Actually, you already know what the compact object is, because I gave you a problem on compact objects in the second assignment, but I will repeat all the definitions. So definition is several parts. So let's first of all assume that T is a triangulated category with small coproducts. So with small coproducts. So first, an object, let's call this C, in the triangulated category T is called compact. If the canonical map from the direct sum over I of Holmes from this object to any family of objects Ti to be home from the C to the direct sum of Ti. So we have for any family of the objects Ti, we have such canonical map. This canonical map is isomorphism. If the canonical map of this is an isomorphism. So in simple terms, the object is compact if the home in this object of the first argument commutes with direct sums, or preserves the coproducts. So two category T so category T is compactly generated. I think I just broke this thing. This is a plastic piece. No, it's gonna be sorry. The side of it broken down. So category C is compactly generated. Maybe I'll write this in words. Is generated, for shortness I'm going to write just CG. Compactly generated if there is a set of compact objects, a set, let's call this T, compact objects, such that when you compute the homes from T to the X and they are all equal to 0 for any little t in the set T. So this implies that actually object X is isomorphic to 0 in the category. Well, there is also a third part of the definition, which is kind of a little bit silly. So a set T is called a generating set. Just for completeness, we don't really need this to prove anything. Of T. If you have two conditions, so if first the condition 1 is the same as before, then the home Tx is equal to 0 for any T in the T implies that the X is isomorphic to 0 in the category, and the second condition is that T is closed under shifts. Of course, this is an immediate remark that whenever you have some remark, so any set of compact or not compact, so any set of compact generators, and by generators I mean this condition, so condition in the 2 or condition 1 and condition 3, so can be turned into a generating set by the trivial procedure. You just take this set of generators that you, for example, have in condition 2 and add all the shifts. You take the union over all integers of the T shifted by P, and the T are all objects in the large T. Okay, so give me an example of a compactly generated category. Compactly generated category. What's the simplest possible example of such category? Yeah, a little bit more general. So the derived category of the ring, which is just a short notation for the derived category, say of the left modules or right modules, is compactly generated okay, and Y was the generators in this case, so I need this set T of generators, so I need to write that the T is equal to something, so with T, what was your idea? What's the generating set? Oh, you can, I think you can just take just one copy of R, right? If you want this to be closed under shifts, you need to take all the shifts of the R, but I think R is enough, right? Oh, maybe wait, maybe
not.
Yeah, so maybe I need to add all the shifts, yes. Well, that is because if you have any complex and all the maps, if you try to compute, say, homes from R to any complex, let's call this maybe C, right? Well, you can identify this just with the C, right? The home over R from the ring to the complex is just the complex. Right? If all the complexes are equal to 0, but all such homes are equal to 0, well, if just one home is just equal to 0, then this means that the complex itself is 0. So I think you don't really need shifts, right? You compute home from the ring to the complex, the size also to the complex.
No, this home is simply some R module.
This is a complex of their module. C is a complex.
But in the definition we have homes, not inner homes, but some abelian groups.
Sorry, what?
In the definition we have homes, simply abelian groups.
Yeah. So yes. Yes. So this is home. This is ungraded home. Yes.
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 So there we have simply C 0. Or not even C0, but some.
It's more like kernel of D0.
Yes.
Yeah. Yes.
This is home
In the derived category.
no, then it's just zeros homology of C.
Well,
Yes.
maybe we can do this as a computation. So this is, you're saying that this is A0 of C, right? Well, but you have something like C0, then there is C1, something other, C minus 1, then there is R, and then you want, so here of course, the rest are just 0. So you want a map to the C0, right, such that the composition, so this is D0, right, such that the composition with D0 is 0. So you actually, if you have such a map, you're choosing an element here. Oh, this over the ring, so we can talk about the elements. So these are elements, say this F is the same as the F of 1, which is just X in the C0, such that D0 of X is equal to 0, right? And if you also take D1, so suppose you have X, which is equal to the D minus 1 of some Y, right? So you're saying that somehow if I take an X of this form, then this is a 0 map? Yeah, because in this case this is quasi-isomorphic to, what would be the right thing to say? If I choose X to be of this form, X
Then we can write homotopic.
yeah, so then kind of you have a map here from the ring to the C minus, which is kind of the sense 1 to the Y, right? So then this map is homotopy. Yeah, so then this map is homotopy equivalent to the 0 map. And of course, if this is 0 in the homotopy category, this is 0 in the derived category. Yeah, so it looks like if you compute just some homes like this, you just get the homology. But if you do this with all the shifts, right? So I think this is something like h to the minus p of c, right? So if you say that all such homes are equal to 0, it means that in the complex all the cohomology are 0. Hence this is a cyclic complex close 0 in the direct category. Okay, so there are some observations about this. Well, there are some simple observations that I think. Yeah, first of all, let me fix the notation. Notation is that the TC, this is full subcategory of compact objects. Okay, so then there is a lemma such that if you take an object C, which is a compact object in template category, then the home from this compact object to the homotopical limit of some diagram is isomorphic to the limit of the homes. Right, so here x, say n, is a directed system. Right? So I think that was an exercise in the second partnership, right? It's not really something new. So prove this exercise. And there is one more lemma which is also kind of tautological. I want to leave this as an exercise. It says that the subcategory of compact objects is a triangulated subcategory. Well, in fact, we can say better. We can say that this is a localizing subcategory. So it is a localizing triangulated subcategory. So now I want to fix some setup that I'm going to use for the end of today's lecture and also next week. So I want to assume that I have S, and unfortunately I don't know how to write handwritten S, because I want to distinguish situation like in the definition there is a category T with one notation for the T, and there is a kind of set of objects inside T. So I want to say that this kind of curly S is a compactly generated triangulated category, and set S inside this curly S. So this is supposed to be a set of compact generators. So is a set of compact generators. Now I want to take R, so is a set of compact objects. Right. So any set of compact objects, it's not related to the S. So just take any set of compact objects, and then you can define subcategory R, which is by definition the localizing closure of the set R. And then there is a quotient functor. So I'm going to call this J with the upper star. Okay, notation coming from algebraic geometry. So this is from the category S to the category T, which is by definition the quotient of the S by the subcategory R. So this is the setup I want to use for some time. So whenever I'm talking about the S, curly S or just S, T or R, with two different forms, it means that something from this setup. So there will be several statements about this. Okay. And the first statement is the following lemma. So for any x in the S, there is y in the right orthogonal to the R, and the map f from the x to the y in more R. Okay. So proof. So I want to define sequence of objects by induction. So we define xn by induction, and x0 is by definition just x. So let I be the set of all maps alpha, say I, which is from the object Ri to the xn, and Ri is an object in the set R. So then I can form a distinguished triangle. So I take the sum of all such Ri's over all elements in the set large I. So then there is a canonical map from the coproduct to the xn. And I take this map and complete this to a distinguished triangle. This gives me object xn plus 1. And I also want to call this map J with the index n plus 1. So this distinguished triangle can be used to define objects xn plus 1 if you already know object xn, and you can do this since x0 is given, then you do this by induction. And by definition, I want to take y to be the homotopical limit of the xn's. So we can notice that these maps that I have in the definition, Jn, so all such maps are isomorphisms in the quotient category. So when you take a quotient of the S by the R, right? Well, because this direct sum of Ri's, this is in the category R, so the quotient they are just 0, so this maps has to be isomorphisms. And then you have kind of very simple observation that you have two directed systems. One directed system is just you have x0 identity, x0 identity, x0, etc. Then the other directed system is x0, j1 to the x1, then there is j2 to the x2, etc. So here the first map from one directed system to another is identity, the second map is j1, and the third map is the composition of the j2 and j1, etc. So we can continue like this. So these two directed systems are isomorphic to directed systems are isomorphic in the S modulo R. Hence, the conclusion is, well, of course, the homotopical limit of the first directed system is x0, the homotopical limit of the second is y. So the conclusion is that there is a map from the x0 to the y, the homotopical limit, which is an isomorphism in the S modulo R. So we have a distinguished triangle. We have x, which is the same as x0. There is a map from the x to y. We complete this to a distinguished triangle for this object C, and then everything shifts. So since this map is an isomorphism is in the S modulo R, we can say immediately that the C is in the R. So what we want to show next is that the object Y is this colimit of the X. This is in the right orthogonal in the R. Okay, to do this, for any little r in the set R, which is just a subset of compact objects, well, I need to rewrite this. So, and then we apply the form from this object R to something to the distinguished triangle where we have and the distinguished triangle. Maybe let me call this distinguished triangle star in the beginning. So then I apply this to the star. So apply this to the star. So then I'll get form R I. So this is direct sum of such forms. Right, so since R is a compact object, I can pull out the coproduct, and this will give it to the form from R to the Xn, and this is of course mapped to the form from the R to the Xn plus 1. Okay. So, but I claim that just by looking at this distinguished triangle that defines Xn plus 1, that this map that I have here is 0. Do you see why the map is 0? You can think about this game, one of the key steps of the book. Why the map is 0?
Because the composition must be 0 and go through all the maps.
Yeah, because this little r is one of the compact objects, right? And all the compact objects are already in this sum. So this little r is one of the sums in that sum. And hence, if you consider a map like this, then you get the composition which is 0. So this form by the construction is, so this map of forms is by the construction is 0. So then it means that if I want to compute the form from this little r, the homotopy element y, I know by lemma that I have as an exercise that this is the same thing as the colimit of the forms from R to the Xn, right? But now we take a colimit of some directed system in which the forms are just 0 maps. Hence, this colimit is just 0. But this is what we want, right? We want to show that y is in the right orthogonal to the R. So we have this. Okay. Yeah, I think I don't have time to prove anything else, so maybe let's stop here for today and continue next time. So the goal for the next time is to prove several theorems about the setup. And by the way, this setup also has a special name. This is called the Thompson localization. So you in general have Verdier localization. If the Verdier localization has a right, it's called Boston localization. And if you start with a complicated generator category, take a quotient by a law of some set of compact objects, this is called the Thompson localization. In particular, you will see that also a Boston localization. So this is what we'll do next time, and probably, so this will be for the first hour, and for the second hour, we'll start algebraic geometry. So maybe some other She will start from the beginning, but then she will be more complicated. Okay, that's all for today.
Любая прямая сумма компактных объектов – это компактный объект.
Это правда?
Ну, если вы хотите, если вот та вот цель,
Утверждение, она толстая, толстая, не очень. Да, yeah, so the little correction, the subcase TC of all components is not localized. I meant to say this is the subcase the direct sum of the component of the component.
Что еще раз вы сейчас сказали про...
Я говорю, что если мы вернул лему,
Да,
который сказал, что компактный объект образует образующую категорию.
да.
Надо было сказать, компактный объект образует толстую категорию.
Да.
В том смысле, что прямой свод n компактного объекта снова компактный, а предположенная прямая сумма компактная, не обязательно компактная.
Да. То есть заменить локалайзер на сик. Нужно этот элемент заменить локалайзер на сик. А можно еще вопрос про инкоинъективные и компаративные резервенты? Вот мы, когда хотим определить производные пункта, нужно построить adapted класс или что-то подобное. И в случае, например, если есть функтор, который точный слева, тогда можно написать из инъективных объектов резольвент, вот они будут образовывать для него adapted класс. Да.
Я доказал, что производные функторы.
Да.
Там было утверждение, что когда берется общий вид для последования,
Да.
там было такое утверждение, что если для любого функтора
Да.
C правый ортогонал является адаптированным классом.
Вообще для любого функтора.
Вообще для любого функтора.
Да.
Вот. Но в случае, когда у нас как бы обычная домовая алгебра,
Вообще для любого функтора.
вообще для любого функтора.
Да.
Вот. Но в случае, когда у нас как бы обычная домовая алгебра,